Welcome to your video on binomial distributions. Before we actually start with this page, I'm going to do a demonstration with you. You do not need to copy it down, but please do watch it. It will show you how the formula for binomial distributions is developed. So here's the example we're going to be working with. It says Billy Bob's messy sock drawer contains 25 black socks and 75 white socks. Billy Bob will be drawing socks with replacement. And this is the important part. It's with replacement. The hypergeometric distributions that you looked at before had no replacement. So these binomial questions, binomial distributions, have replacement. X is the number of black socks, so it's important that everything is done in terms of the number of black socks. So if he's only drawing one sock, he has a 25 out of 100 chance of getting a black sock, or we can write that as 0.25, which means he has a 0.75 chance of getting a white sock. So this branch here would represent 1 black, 0 white, and this branch would represent 0 black, 1 white. So for no black socks, there's 1 branch favorable, and for 1 black sock, there is 1 branch favorable. So right now we're just looking at the number of branches. Now, if he drew 2 socks, then there's still the same probabilities because there is replacement. But now if you look at the number of branches, this branch here would be 2 black, 0 white. This branch here would be 1 black, 1 white. This branch here would also be 1 black, 1 white, and this branch here would be no black, 2 white. So again, if we took a look at the number of branches, there is 1 branch that had no black, which is here. There's 2 branches that had 1 black, and there's 1 branch that had 2 black. Now in Unit 2, that's as far as we went, which was drawing 2 items. Now what we're going to do is what happens if you draw 3 or 4 or 5 or even 10 socks. So if you drew 3 socks, this branch here would be 3 black, no white. This branch here would be 2 black, 1 white. This branch would be 2 black, 1 white. This one here would be 1 black, 2 white. This would be 2 black, 1 white. This would be 1 black, 2 white. This would be 1 black, 2 whites. And this would be no blacks, 3 whites. So by looking at the number of branches, there is 1 branch that has no black socks. To have 1 black sock, we've got 1, 2, 3 branches. To have 2 black socks, we have 1, 2, 3 branches. And to have no black socks, to have 3 black socks, you have 1 branch. Are you starting to see maybe some pattern in these numbers? Let's take a look at 4 socks now. So to conserve space, I just wrote down the number of black socks, not the number of white socks. But to get 0 black socks, there's just this 1 branch here. To get 1 black sock, there's 1, 2, 3, 4 branches. To get 2 black socks, there's 1, 2, 3, 4, 5, 6 branches. To get 3 black socks, there is 1, 2, 3, 4. And to get 4 black socks, it's just this one branch here. I'm hoping by now you can really see the pattern and can estimate what's going to happen when we draw 5 socks. Okay, this will be the last one we do. And I've conserved space even more, so now I'm just writing down how many black socks there are here. So to get no black socks, you just have this one branch. To get 1 black sock, you've got 1, 2, 3, 4, 5 branches. Can you think of what number goes here? 2 black socks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 branches. Now how many branches do you think there will be for 3 black socks? Let's see if you're right. 1, 2, 3. Oh, I think I lost count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many branches do you think there are for 4 blacks? Let's count. There's 1, 2, 3, 4, 5. And lastly, for 5 black socks, there's just this one branch. So hopefully you can see that these numbers follow Pascal's triangle. So let's take a look at this example. What is the probability that there will be 2 black socks and 3 white socks? So if there's 2 black, the probability of a black is 0.25, and there's 2 of them. And there's 3 white socks, so the probability of a white sock is 0.75. But then we need to know the number of branches that satisfy this condition. So the number of branches for 2 black socks would be 10. So you would have to multiply this by 10. So the probability that the number of black socks is equal to 2 would be equal to this. So you have to make sure that you multiply these probabilities by the number of branches, because there are 10 different ways that you can have 2 black socks and 3 white socks come out. And a shorter way you could have written this is you've got 10 times, since you're multiplying 0.25 twice, it's 0.25 squared, and you're multiplying 0.75 3 times, so that would be 0.75 to the 3. So that would be the shorter form way of writing this expanded work. This is when you can start copying down into your course pack. So the example is, a bag contains 8 red and 4 blue marbles. 5 marbles are drawn with replacement. X is the number of red marbles, so make sure you know what we're talking about. Determine Px equals 3. So what does this mean, Px equals 3? If you read the symbols, it's the probability that the number of red marbles is equal to 3. So if you're drawing 5 marbles, that means you have to have 3 red and 2 blue. So the probability of a red marble, there's 8 marbles out of 12, and we need 3 of those. The probability of a blue marble is 4 out of 12, and we need 2 of those. And then now you have to decide how many branches. So if we're looking at 3 red marbles, that's essentially the same as the 3 black socks. It's here, the number 10. So you would have to multiply that by 10. And that works out to 80 over 243, or as a decimal, that would be equal to 0.329. So remember, fraction in lowest terms or decimal to 3 decimal places. So the question is, what if we draw more than 5 marbles? What if we draw 10 marbles? You don't want to have to be doing this 10 times. So what I want you to remember is that this here is row 1. This here is row 2. This is row 3. This is row 4. And this is row 5. So if we are drawing 5 items, you use row 5 of Pascal's triangle. So the row number is equal to the number of items drawn. All right, and this one here is term 0. This one here is term 1. This one here is term 2. This here is term 3. And this is term 4. And this is term 5. Remember that you have to start your terms at 0. Technically, we have to start our row at 0, but that would be a case of drawing no socks, so that didn't really have any relevance to our question. So the number of items that you draw is the row, and to get the term number, if we wanted 3 black socks, or if we wanted 3 red marbles, then that's the term number. So the term number is the value of x. And x just means the number of favorable outcomes. So again, you don't have to write any of this down because we're going to summarize it all in the note. The last thing you have to remember is if we want to draw 10 socks, we don't want to have to continue this row 10 times. We also don't have a nice big Pascal's triangle for us to get to row 10. So what I want you to remember is that any term, so for instance this term here, can be found using NCR. So N is the row number, which is 4, and R is the term number, which is 1. So if you tried 4C1 in your calculator, you're going to get 4. So the number of items, we use an N, and the number of favorable outcomes, we use an X, and that will give you the number of branches. All right, so let's go back to the note and summarize all this. So in order to get this 10, you had 5 marbles drawn, so that is your N value. We were interested in 3 favorable outcomes, so that's your X. So that 10 was actually found by 5C3. So as we said, hypergeometric deals with cases that have non-replacement. Binomial distributions have cases where there is replacement, but it's also more than that. The binomial distribution deals with Bernoulli trials, and I'll explain what those are. In order for a distribution to be binomial, there can only be two outcomes. So red, blue, or you could say red, not red. So the one that is x, the variable that is x, is what we call a success, and it is labeled with a P for some reason. And the other one that we are not measuring is called a failure, and that one we call Q. And the second point is that each trial is independent. So if you are drawing items, there must be replacement. So those are the two conditions that must be met for there to be a binomial distribution. So the probability distribution of the number of successes in a sequence of Bernoulli trials is called the binomial distribution. So here's the formula. The probability of your random variable being a particular value is, first thing we need is the number of branches. So that is the number of trials, that's the row number, C, X, which is the number of successes we're interested in. That's multiplied by the probability of a success to the exponent of how many successes we want. And that's multiplied by the probability of a failure. And its exponent is how many trials are remaining. So in this example, there were 5 trials because there were 5 marbles drawn. We're measuring 3 successes. This is the probability of a success, which is a red marble, and we wanted 3 of them. This is the probability of a failure, which is not being red, and there were 2 left over. This was the 5 minus 3. So that's where that formula comes from. To get the expected value, it's similar to the hypergeometric. What you're doing is you're taking the probability of a success and you're multiplying it by the number of trials. Or some people write it as n times p. It doesn't really matter either way. So we're going to look at an example. And I said, if you're drawing things, you need to have replacement for it to be binomial. But not all binomial questions deal with drawing things with replacement. The condition is that it just has to be independent, which means the probability in each trial stays the same each time. Rolling a die, flipping a coin, those are both independent events. So those would also be binomial distributions. So a die is rolled 10 times, and your variable is what we're measuring. It's the number of times you roll a 2. So we're going to determine px equals 4 and ex. So this is the probability that you roll a 2 4 times out of the 10 times that you've rolled a die. So n is the number of trials, which is 10. X is the number of successes we're interested in, which is 4. P is the probability of a success. So this here is a success. So the probability of rolling a 2 is 1 over 6. And the probability of a failure is not rolling a 2, so that would be 5 over 6. So the formula is NCX times p to the x times q to the n minus x. So this is the number of branches, and that's the probability of getting a 2. We want 4 of them. That's the probability of not getting a 2. We want 6 of them. So that is equal to 0.054. The expected value is n times p. So n is 10. There's 10 trials times p, which is the probability of success. And 10 times 1 over 6 is 1.67. So on average, if we were continuously repeating this, rolling this die 10 times, you would roll it to 1.67 times. And that's how you work a binomial distribution question. All right, so let's look at the next example. Suppose that Bianosthol, which is a new drug, is effective in 65% of clinical trials. Suppose there are 10 trials. X is the number of times the drug was effective. Determine the probability that the number of times the drug was effective is less than or equal to 2. This is also independent because there's a 65% chance of one person having the drug be effective, and then there's 65% chance of another person. So whether the drug was effective in the first person does not change whether the drug was effective in the second person. So this is also independent, making this binomial. So n is 10. There's 10 trials. X is, we want less than or equal to 2. So there's 0, 1, or 2. P is the probability of success. Remember, whatever X is, that's your success. So the probability that the drug was effective is 0.65, which means the probability that it's not effective is 0.35, because those two things have to add up to 100% or 1. So that means we need the probability of no successes plus the probability of one success plus the probability of 2 successes. So no successes, so that would be 10C0 times 0.65, we want no successes, 0.35, we want 10 failures. For there being 10 trials, see 1 success. Probability of a success, we want 1 of them. Probability of a failure, we want 9 of them. Now to have 2 successful, 10C2. Probability of a success, we want 2 of them, times the probability of a failure, we want 8 of them. And in your calculator, all of that works out to 0.0048. Now, if you think you get it, you can move on and try examples 3 and 4 on your own. If not, I'll do example 3 with you, and you can try example 4 on your own. So, a bag contains 2 red, 3 blue, and 4 green balls. A ball is drawn and replaced 6 times. X is the number of green balls drawn, so that's your success. Determine the probability that the number of green balls is at least 1. So n is 6 because we are drawing it 6 times. X is, because it's at least 1, you could have 1, 2, 3, 4, 5, or 6. You might be asking, how could you have 5 or 6 green balls when there's only 4 green balls available? The answer to that question is, you have to remember that it's replaced each time. So it is possible to have 6 balls. Probability of success. So the success of a green ball is there's 4 green balls out of a total of 9 balls. And the probability of failure is not green, which would be 5 out of 9. Now, just like units 1 and 2, the at least one case can be found by taking the total probabilities, which is 1, and subtracting the only case we don't want, which is 0. Alternatively, you could have found the probabilities for each of these and added them up like you did here, but that would take a long time because then you'd have 6 cases. So anytime you have at least one, it's the total, which is 1, because the total of all your probabilities is 1, minus the case we don't want, which is 0. So it's 1 minus, there's 6 trials, we want no successes. So the probability of success, we want none of them. The probability of failure, we want 6 of them. And that is equal to 0.971. Make sure you're rounding properly. Okay, I would like you to try example 4. Make sure you're looking at most. At most means you can have 0, 1, or 2. So try this example on your own, and then when you're finished, come back and check your answers. So press pause now, please, and check your answer after you've actually tried it yourself. Press pause now, please. Okay, welcome back. You can check your answer. Because we are measuring how many trees are diseased, that's what your variable is. There's 12 trials. As we said, at most 2 means 0, 1, or 2. The probability of success is being diseased. The probability of failure is not being diseased. And you're going to use your formula 3 times for no cases, no successes, 1 success, and 2 successes. So before we end off, there are some shortcuts that you can take in your calculator here rather than typing all of this in. For instance, 12C0. Any number C0 is equal to 1, because that would be the first term of each row in Pascal's triangle, and the first term in every row is equal to 1. So if you have any number C0, it's equal to 1, so you really don't have to do that. Anything with an exponent of 0 is also equal to 1. So you could skip this as well. Last one, 12C1. Anything C1 is equal to whatever the row number was. So 12C1 is equal to 12. 6C1 is equal to 6, because that would be the second term in each row, and the second term in each row is always equal to the same as the row number. So in row 8, the second term would be 8. So if you were calculating this, the only thing you'd have to type into your calculator is 0.92. And anything with an exponent of 1 is just the same. So you could have just put 0.08. You don't have to do 0.08 to the exponent 1. So before we conclude, there's a couple of things that I didn't do that I really need to go back and do for communication. So what I did not do is any of my approximately equal signs, and I didn't do therefore, the probability, is approximately 0.935. So sorry about that. So we're just going to go back and fix those things up on each of the examples. So again here, and fix that up on this example here. So approximately signs and a therefore sentence. For example 3. Then example 2. Just fix up example 2 there. And example 1. So you've got approximately symbols for both the probability and the expected value, and therefore sentences for both of them as well. So that was example 1. And we should also just finish this initial example as well. And just, again, fixing that up there. Alright, so sorry for this really long and boring video, but unfortunately this is actually quite an important lesson, and it will come back in the final video, not the next one, but the final one. So just make sure that you remember about binomial distributions. It's important to remember when you can use a binomial distribution and what the formula is, because we will be touching on this again in the last video. So if there's anything you didn't understand, make note of it and ask your teacher the next day. Thank you. So sorry this was a bit of a